It's time. All right.
All right, just to give a moment.
Is my sound level good?
I think it's good. It's good. Yeah.
Uh,
Okay, and to the audience, please let us know if there's any audio problems. Last time we had echo, so if there's no sound, there's echo, please let us know.
we're live.
Oh, okay. Okay. All right. Hello, everyone. Welcome to Corecast. I am your host, Tim.
Mikey.
And this is Sahil. Welcome everybody to a brand new exciting episode of Quirkcast. Before we get started, as usual, if you haven't already, do join our Discord channel. And if you're watching on YouTube, where we do this every Tuesday, 5 p.m. Pacific, 8 p.m. Eastern, do ask us questions in the episode and we'll get to it. Also, we're in the process of making shorts, so if there's any 1 minute or less sound bites that you'd like to hear us explain, discuss more about, do let us know as well, and we'll consider making those. So without further ado, let's get to it. So Tim and Mikey, this is an interesting episode. I mean, this is probably one of the first things I heard in terms of like science and philosophy, the notion of turtles all the way down. We'll discuss what that means in a moment. But essentially, I guess it ties to zooming in physics. So, I guess, Tim or Mikey, I'll let you guys take it away and like explain what turtles have turtles all the way down has to even do with physics. Turtles are like these biological animals with shells. Why are we even talking about turtles all the way down?
It's actually a great story. I might get some of the details wrong, but yeah, I didn't realize this before too. That like the phrase "turtles all the way down" is kind of a mainstay in philosophy. And my sister got a PhD in philosophy, and some of her classmates wrote papers about this concept of turtles all the way down. But um, I guess as the legend goes, this phrase started from a public lecture that was being administered by the great luminary academic scholar named Bertrand Russell. I believe it was in Princeton, actually, sometime in the late 30s, that Bertrand Russell was giving a public lecture. Um, so like people from all walks of life were welcome to attend, and it was just to cover like the basic sort of like, and these were relatively recent findings. So I think the topic of the lecture was, recent discoveries in astronomy. That the solar system is made of a star with orbiting planets, and collections of stars make up galaxies and all this stuff like that. And he described, trying to describe something about the large scale structure of the universe, or as much about it as we knew back then. And I think everything was all well and good, but apparently at the end of this lecture, um, by all accounts, the most adorable and cutest old lady uh, walked up to Bertrand Russell at the end of the lecture and said something like, this is a very nice story that you've told, but I'm afraid it's all nonsense. The fact of the matter, the truth of the matter is that the entire universe is resting on the back of a giant turtle. And this Bertrand Russell replied, well, then what is that turtle standing on top of? And allegedly, the old lady replied, well, you're a very clever young man, very clever, but it's turtles all the way down. So it's kind of like in an attempt to explain, like, when we think of reductionism, like everything's made of atoms, atoms are made of protons, protons are made of, we're trying to find the fundamental theory. Um, Maybe at a certain point, you just see a turtle, and maybe after that point, all you see is just turtles and turtles and turtles. Feynman kind of described a similar sentiment, but he described it as like peeling back layers of the onion. You think of like reality as like an onion with different layers, and our attempt at trying to understand it is like peeling back these layers. So it's a similar concept.
I guess, Mikey, real quick, could you give maybe a one sentence description of what reductionism is, like more
Yeah.
formally?
Yeah. So just really simply, reductionism is an idea in philosophy that the best way to understand something is by understanding its constituent components. That you can understand the whole best by understanding the pieces that make it up. And I guess it's sort of
Mhm.
like at odds with a philosophy called emergentism, which believes that you have to look at everything holistically in order to get a picture. Yeah.
And I would
I
say
guess you
that,
could say, Oh, I'll just add one thing real quick. You could probably say that reductionism works well for like things like a watch. If you understand each
Yeah.
individual gear of a watch, and then construct it back together, that helps you understand it better.
Reductionism is underrated. I mean, the amount of like just human progress that has been born out of this just one philosophy is tremendous. And I think people like I get it, like people want to be contrarian and they want to like try to undercut the significance of these things, but it's really just tremendous, I think.
Go ahead, Tim.
Yeah, and I would say in particle physics, these ideas can actually be made precise. Of course, it's not exactly, in the philosophy sense, turtles and whatnot. But in particle physics, I think you can argue that they are structures, and these structures are really just particles. And we literally have a way to formalize what zooming in means. And in the world of quantum physics, zooming in usually is associated with high energies. As we repeated many episodes, in order to probe deeper, you need high energies.
Usually, that's pretty much a strict correspondence, right?
Sure. 99, yeah, it's pretty as true as gravity. Although a caveat on that, we'll talk about that. Why it's not. Sometimes even that breaks down. But still, I think it's fair to say that the business of fundamental physics is to study stuff, and throughout history, we keep seeing this idea keep playing out. Like people thought the protons were fundamental. Then lo and behold, when they smash protons at high energy, they can kind of break it apart, and they found out that protons are made up of quarks and gluons. We have built high energy colliders, and the hope is that maybe as we smash even quarks and gluons, maybe we'll find some other stuff. Maybe constituent is a strong word, but the hope is that by smashing things at higher and high energies, we don't exactly break it apart, but kind of we see more and more structures that are, that are more and more layers and layers of structure coming up. So this concept of turtles all the way down could be quite relevant in particle physics.
So these layers of reality are the turtles, just so it's clear to the audience.
Yeah,
like a turtle being an analogy for different structures that you might find as you probe deeper and deeper into the nature of reality.
Yeah, specifically, these are different particles, basically. That's what we're referring to.
Got it. So in this example, like you talked about, probing particles at higher energies, either can be smashing or shooting, particles at other particles, effectively colliding them at higher energies to probe the smaller scales. If we go to this analogy about turtles, it seems like they're just the same turtle, but larger. So in the story you gave, Mikey, it's like, well, it's just all turtles all the way down. But here we clearly see it's not like protons are made up of like smaller protons, which are made up with smaller protons. It's a completely different thing. So I guess, how do you, is there such a notion as like turtles all the way down, like actually the same thing that makes up the thing itself? Or I don't know, it's kind of like, I don't want to say recursive, but maybe I'm leaning towards that, but just like similar sort of thing.
Yeah, like I guess the most obvious example of that is like when we're in high school and we notice that the Bohr model of the atom looks a lot like a solar system, and so there's kind of like repeated pattern. And so yeah, you could maybe the solar system is like one species of turtle, and then you look deeper in that, and then maybe an atom is like another species of turtle. But then so yeah, I agree. Like there is a large variety in the species of turtles we encounter as we go down. So yeah, it depends on how far one takes analogy.
Oh, I was gonna say maybe it might be helpful to go over cases of like, because I know we'll probably talk about this a bit more in the episode, but the notion of self-similarity, like how nature uses like structures that look similar to the larger structure itself, and maybe you can give everyday examples and how that appears in physics, and then we can talk about how that breaks down.
I would say sometimes a lot of these self-similar structure in physics could be accidental, but maybe accidental is not entirely accurate.
Well, there's not a lot of options. If you demand spherical symmetry, there's not a lot of options.
Yeah, I mean, I will also say that you can go through all the possibility, right? Like imagine you're zooming in. What should you see? Should you see more and more and more structure? But if you see more, does it mean that eventually you get infinite amount of structure? It's sort of this principle in science that as you zoom in, you tend to get less stuff. Things tend to be more easily explained. And if in the world of science, when you zoom in, there's more and more variable, then science becomes less predictive. Like we shouldn't expect something that's more complicated. So then there's sort of two possibility now. When I zoom in, do I expect less and less and less, and at some point becomes empty, or does this reduction of complexity, does it slow down at some point in such a way that as you zoom in, hey, you don't get any more or less, it's the same. And when that happens, you naturally get a fractal-like structure because you're not increasing or decreasing in complexity. And that's why this behavior actually can sort of accidentally emerges in nature. And I think a good example is like convection cells or something. Or like
what cells?
Convection cells. Like you see turbulence, like air kind of go in circles. And those circles could make bigger and bigger circles. There's a little bit of recursive structure there. And probably like what, broccoli or whatever, those are probably more accidental than anything.
Cauliflower.
Yeah, cauliflower, ferns.
Yeah. I guess that makes sense. So actually, Tim, going on that point, as you like zoom in, you see structure. Take the example of a proton. Originally, like I think people thought it was point-like, with the plus charge, and then when you zoom in, you realize, oh, there's particles inside, and then if you zoom in more, there's just all this stuff happening, and so it seems like it's getting more complicated. So I guess what point does it get simpler, or like is it just how do you sort of reconcile that?
Well, I would say the most basic possibility is let's say imagine the world only has photons, particles of light.
Okay.
If you zoom in, you're just gonna get more particles of light. I guess. Well, if particles of light don't interact, it's almost a trivial fractal. You zoom in, they're just particles of light. Maybe the light. If you zoom in, the wavelength of the light might change and whatnot. But that's one possibility. That's like a kind of like a dumb fractal, if anything. So that's a possibility of a simple turtle all the way down. I don't know if you call that.
Tim, before you go on, jargon alert, use the word fractal. Can you define what that is?
I think we're using it interchangeably with many different words. Fractal is just something that's self-similar. You zoom in, you see the same thing again. Like your hand is not a fractal. If you zoom in, your hand, you don't see the hand anymore. You see cells and whatnot. But if you look at a line, an infinite line, you zoom in, it's the same line. The line is still there. That's a fractal. Or you see a spiral. I don't know, like those infinite spiral, like those hypnotizing spiral illusion. I don't know what you call it. You kind of zoom in, be like, whoa, there's more and more spiral. That's what we're referring to.
Maybe it's worth mentioning at this point. I was like, we didn't discuss this, but like, once upon a time, physicists had a dream called the theory of everything, and the goal of this dream was that like one day we, as we probe deeper and deeper into nature, and we find the universe is standing on this turtle, and that turtle is on top of this turtle. That eventually, when we got down far enough, we would find one ultimate turtle that just rules everything and is just ultra simple. That used to be a fantasy that almost every single physicist, famously Einstein and all these other people subscribe to as well. And it's a question whether or not that fantasy is a plausible reality. But that's really what we're discussing here, the theory of everything.
Got it. Tim, before I interrupted you, you were talking about you were saying.
Oh, I lost my train of thought. Yeah.
Oh, sorry.
just keep going. Yeah.
Okay. So I guess the question I asked is like, does it keep getting more complex? Will it stop at one turtle, like the big boss turtle at the end of the road, or does it just keep going forever? Like, I mean, is there any reason to expect it to even stop?
I do want to mention, I don't know, Tim, do you like, I would push back against the idea that it gets more complex. I think from everything we've seen so far, as you go down, it does get simpler, even though it seems complicated because when you break protons, you get like kind of a messy soup.
Mhm.
But the rules that are supposed to determine that soup are much simpler than, say, the rules that like determine how combustion works on a macroscopic scale, for example.
No, but
Mhm.
I agree. I'm just saying that we should expect the real complexity to reduce, right?
Yeah,
But at
yeah.
some point, when does this reduction end? Because if you keep reducing in complexity, are you just gonna have not end up with nothing, right?
No, but that is the idea of the theory of everything, right? That there would be just one simple unifying
Yeah, and that's the
equation, and
end.
that would be, yeah.
Wait,
But
I'd like to challenge that a little bit. So, for instance, like when you talk about things getting simpler, are you talking about like a more accurate description? Because if I take like, say, a more macroscopic description of water, like water waves, I can model it very simply as just like, it has
Yeah.
this frequency at which it oscillates and ignore all the tiny little molecules. But if I zoom in and I see all the little molecules interacting with each other, I've introduced this extra complexity that I can't simply just like, ignore any longer. So what gives with that, for
That's a
instance?
great example. I would say that
Mm,
when we say simplicity, we mean the ability to describe a greater range of phenomenon with a smaller number of parameters, um,
mhm,
in a way that is like not like, because the example you gave, like, yeah, it's you can approximate waterways, but through very simple means, like on a macroscopic scale. But if you're not resorting to an approximation and you believe what you're doing is exact, and you can get more range of predictions with smaller parameters, I would say that that would be the qualifying definition of simple.
so can you give me an example in this particular context of it doesn't have to be too technical, but like
yeah,
for
I think
example of particle physics? Yeah.
for example, if you look at you can develop a theory of sound, right? Like sound waves,
Hmm.
how fast sound wave
Yeah.
is moving. The theory is very simple. You just need to give it's just a bunch of wave equation. You can say, well, what's the speed of sound in a particular medium, and
Hmm.
then if you get the wavelength and the amplitude, you can work out, I don't know, sound engineering, right? And that's what we do. But you will never be able to explain why the speed of sound is that particular number, or
Right.
you never be able to get more precise behavior. Like, what if something goes supersonic? Your theory will break down. You'll be like, well, I can't take into account shock waves because your theory doesn't take that into account. If you go to a more fundamental theory, you describe the individual particles of air. Sure, it's very, very complicated. Like, you don't even see sound waves anymore. But from that
Well,
theory,
the
you
rules
work.
are simple. The rules are simple. The
Right.
evolution is complicated.
Yeah, the
Yeah.
rules are simpler, but you should be able to explain, sound waves, shock waves, and a variety of other phenomena from the more basic theory. So that's a good example, I think.
That's a great example.
Mm.
The most basic example is the one that Nemo always gives, which is like, just the idea that the same force responsible for pulling apples to the ground is the same force responsible for making the moon appear to go around the sky is like, you can explain both those things with one theory, which we call gravity. That's very powerful, right? Two things that seem to have almost nothing to do with each other being explained by a common theme.
Yeah, that is interesting. That makes sense to me. I guess then like if let's go through the example. Let's say you zoom in, you keep zooming in. We've discussed a number of episodes in the past that eventually there comes a limit in terms of how you're zooming in that you'll hit like you can't go any further and has to do with the black hole forming. And for those interested in how that happens, do check out our previous episodes on that. But you reach this limit. So does that mean the question is unanswerable or like, yeah,
I,
just is it turtle all the way down or yeah.
yeah, I would say,
We were
when
discussing this just before. Sorry,
yeah,
continue.
I would say when quantum gravity is involved, the notion of zooming in changes. I know we talk about a lot that zooming in is equivalent to higher energies, at least in
Mhm.
ordinary life. But something weird happens when you have quantum gravity, because at some point let's go to this analogy again. in order to probe closer distances, smaller distances, you send more and more energy. At some point, you create a black hole. And then if you try harder, because a black hole, you can't see what's inside a black hole. And you try to put more energy and be like, you know what? I still want to try harder. The black hole all of a sudden get larger. So you all of a sudden, this relationship between energy and size, initially it's like high energy, smaller size, but it becomes nonlinear now. At some point, higher energy means all of a sudden you reach a minimal size and the size goes back up again. So I would say this naive notion of zooming in terms of space does break down. And if your turtles going down means zooming in, then it's definitely not turtles all the way down. I think we can definitively say that. It's not turtles all the way down if you just zoom in onto space and time.
So does that mean, like, I guess initially we were describing the turtles in terms of space and time, but now, like, when you go below a certain limit, it's not even space and time, it's like
black
some
holes.
funky turtle.
It's like black hole turtles, if that's a thing.
But that's if you're still describing space and time. But if you want to, like, I mean, clearly, I would conjecture that both of you believe there's something beyond that. It's not just like space and time is not the end. But I guess, like, what would it be? Or I don't know if we want to go down this train of thought.
I mean, there's a clear answer, right? In physics,
okay,
this act of zooming in can be elevated to be something, I guess, more beautiful. And that elevation is to symmetry. So if instead of, if you take the act of zooming in, the next level, so turtle goes all the way down means turtle going to some symmetry down, whatever that means.
Or like the turtles start looking more and more identical as you go down. They start being copies of the same turtle. Is that fair?
Yeah, it's of course it's a lot more abstract.
Yeah, we're trying to make an analogy with turtles here. It's difficult. I agree.
It turns out that if you buy string theory, let's say if you believe in string theory, that symmetry has to be enforced. So if you believe string theory is the true description of the universe, then in some weird way, string theory is turtles all the way down. So that's the interesting bit.
Just for the record, we generally all do believe that, right?
Yeah, I think so. It's our best guess right now. Like, maybe it's not exactly correct. Like, it's like...
You just can't avoid it.
Yeah, it's like 80% there. Yeah.
If you try to avoid it, you're going to run into it.
Yeah, actually, okay, so on that note, I mean, doesn't string theory say, like, strings are the smallest objects? So clearly, like, the last turtle would just be the string itself, and you're done? Is that it?
That's where some of the properties of string theory comes in. String theory...
But the string has turtles inside of it.
So for those of you who are unfamiliar with string theory, I'm also not too familiar, not an expert, but string theory is also not exactly a complete theory. We believe that string theory is it's sort of an emergent theory from something more fundamental, the M theory. Nobody knows what that is. And because of that, string theories has relationship. Different versions of string theories are linked together by something we call duality. So I know this is all technical, but one of the interesting duality is called colloquially the small large duality, or the T duality, right? It means that if you take one string theory, you take a very small string, and you make it really large. Instead of size, you have one over the size. You actually have kind of the same string theory, and this is similar to the behavior in gravity, right? Like you put in more energy. You got a black hole. The black hole actually gets larger. So high energy now links to larger radius as opposed to smaller radius. And somehow if you flip that around, string theory tells you that string theory kind of stays the same. It's still string theory. So string theory itself has this backward, inside out, upside down, weird zooming in behavior. And if you buy that, that's turtles all the way down, I think.
Wait, no. So that's my question. Wait, is that turtles all the way down? Like, so what does that mean in terms of turtles?
I think you go back and forth, right? You go.
Doesn't that mean that there's just a relationship between the turtles at the top and the turtles at the bottom? There's like an equivalent.
It's like a turtle ring, right? Metaphorically, like turtle, oh, back to the first turtle, turtle, back. I don't even know how to think about that.
I feel like the true actual like colloquial description is that like these turtles are actually the same turtle, right?
Yeah, actually, that's the kicker. In particle physics, sometimes you see a symmetry, but when the symmetry gets so elevated, it gets elevated to what we call a redundancy. So it says because all the things are so equal that they might just be different aspect of the same thing. So if you believe that, maybe there isn't turtle all the way down. It's just a mirage of turtle. They're just one turtle. And there's
just one turtle that's projecting itself.
It goes around and around and around because of these duality, redundancy. So I mean,
certainly the relationships between these turtles is intensely intimate, and we don't fully understand it.
But let me add that in our universe we don't see it. Because I want to emphasize one thing, because string theory is a quantum theory of gravity. We only have one universe. When you look at string theory deals with all possible universes, right? So in some sense, our universe is only one out of a bazillion possibility. So you're not going to see turtles all the way down in our universe. But if you look at all the possible universes, which you buy string theory, which is or any quantum gravity theory, if you buy that, it's turtles all the way down, but like, you got to go beyond our universe.
But we can see turtles in our universe, like we gave examples, like the solar system is one turtle, and the layer below that, like molecules, is another turtle, atoms is another turtle, or so we see this. But like, yeah, as Tim was mentioning, when we get really, really deep down into the layers, then it's hard to imagine we don't have to consider the sum of all these possibilities, because quantum mechanics typically dictates that we do.
Yeah. So there's an audience question that came in maybe a while back. Why should the tiny eventually terminate? I guess maybe referring to like if you're zooming in and you reach the turtle that's like the tiniest turtle. Although Although in the story it's like a turtle standing on top of a bigger turtle, but here it's gotta be inverted. So in this case, if you're looking at the tiniest turtle, like why should it stop?
Yeah, I mean at the end of the day,
the tiniest turtle has to deal with gravity, which is the biggest.
Yeah, because what is size? If you think about it, size is measured in space-time. And what is space-time? Space-time is made up of stuff we don't know. Hopefully quantum gravity has an answer. So when quantum gravity becomes important, the notion of size stops making sense. So you have to hop onto a different notion. So conventionally, conventionally it terminates at black hole because
and the reason it terminates there is because of the particular strength of gravity that we measure. If you want to call it maximum of the universe or some God-given constant, but that's like the fundamental reason why.
Yeah. I would say we don't know exactly how it happened, why it happened, but like all roads points to a similar problem. The reason we use black hole as an example because it's illustrative. But like this idea that size stops making sense is ubiquitous in quantum gravity, and black hole is just a symptom of it, but it's just a way for us to understand.
That's a good point.
I guess to flip this question on its head, so let's say what we can know is that there is a limit to how much you can zoom in, but what about the other way around? Is it turtles all the way up?
Whoa.
That
twist.
I mean, there have been theories of multiverses. So string the sort of the multiple.
Our picture is actually more appropriate for this zooming out picture.
Yeah. So, but anyway, they're kind of I guess two class of views regarding that. When we talk about quantum gravity, we're talking about possible universes. These are not real universes, right? Because of course we don't know that. These are could have been universes. But there have been theories that talk about literal multiverses, saying that maybe all versions of universes do exist. Of course, we have no way to access it. So then you can zoom out. But of course, when you zoom in that out, once again, the notion of size is also start making sense. Because like, how do you measure something, right? In order for you to measure something, you have to be able to go to one end to the other end and have an observer.
But they have to be causally connected, that's for sure.
Yeah, but like if you have bazillion multiverses, like how large are the? You don't even know.
Causally disconnected. There's no sense. There's no notion of distance there.
There's no notion of sizes and whatnot. Yeah.
So Tim, when you mention the word multiverse, there's many different definitions of that. Can we clarify what you mean by multiverse?
I would say most versions of multiverse are the real multiverse. The quantum. Yeah, the quantum version is usually referred to as parallel universe.
Oh, no, many worlds. Many worlds.
Something like that. Yeah, fake. Yeah. So multiverses usually refer to real universes. Yeah.
Yeah. I would agree with
what does that even mean? What does a real universe mean?
We're not talking about those fake theories. We're talking about the real thing.
Yeah. So those theories are referring to hypotheses on how our universe is created. And basically the idea is that the conditions to create our universe is so generic that there must have been others that also got created. And in fact, infinitely.
It's really hard to stop at one. It's really hard to stop at one. If you're going to make universes, the idea of stopping at one is ridiculous.
Yeah, it's pretty much just either it's zero, you have no universe, you have one universe, or you have infinitely many universes. You can't just...
One is the most ridiculous possibility.
Probably. So, yeah. So in that way, these are, I don't even know, would these even be turtles? They're just multiverse.
No, I think it's a superposition of turtles. It's just an orgy of turtles.
Multiverse turtles? Is that that's got to be?
I really think that our pictorial description of this episode is more appropriate than whatever picture we imagine going into this.
Yeah, just for context, people actually draw circles to represent certain types of space-time. And that's why it does ring a bell. Like circles are kind of representative of these kind of spaces. And yeah, people draw these diagrams. So that makes our title picture accidentally more relevant than we thought.
Yeah, and it's just adorable.
I agree with that. So we've discussed in the beginning of the episode, like particle physics likes to zoom in, and hopefully eventually you'll, I guess like Mikey, you were mentioning at towards the beginning of the episode that, the Holy Grail for a long time was like you stop, there'd be one turtle and that'd be it. But looking at it going the other way around, is there any, I guess, benefit to zooming out that informs like the small in some sense versus like the small informing the large?
It goes against the idea of reductionism, which says that smaller is better for understanding. Because if you zoom out, you lose detail. Right? It's just like a resolution issue. So again, like reductionism seems to have come up against its limits. I think the entire scientific community is kind of struggling to find an alternative to reductionism because for the first time, it seems to be failing us. But so yeah, I don't know. Like I think there are some modern
hold on.
viewpoints on what you described. Yeah,
the viewpoint is much more grim, right? If you zoom out, you're basically saying that our universe is totally trivial. Basically, whatever happens in our universe, just complete accident. The fact that we have the Higgs field, protons, neutrons, electrons, it tells us nothing about fundamental reality because all the possibilities are realized. We're just one out of infinitely many.
Unless the landscape is the truth. that anthropic landscape is the truth, then what you're describing
Yeah.
is
Well, the truth is probably the mixture of these two, somewhere in between the spectrum, right? But I'm saying if you take the extreme version, you just zoom out, there's a huge multiverse. You could argue that look, none of this matters. Like the physics of what we see, it's nothing. It doesn't
but
mean anything.
that could be the truth.
That could be, yeah, that could be. So turtles, if you think it's turtles all the way up, I don't know what you would think. Would you just abandon physics? But there's still some physics worth doing. But
No, at that point it becomes literally like as it becomes zoology, stamp collecting at that
stamp
point.
collecting,
You're just cataloging turtles. But we don't have compelling evidence that that's not the case.
Yeah, I mean, maybe this is a whole another episode, but one thing I was thinking about is this notion of like all possibilities, there exists this multitude of all possibilities that are explored, and we happen to be in, the small slice where we can exist of those possibilities to be able to even ask these questions. But do you think that's due to more of like us from like a human perspective and the small slice we're able to observe versus versus there is no notion of possibilities, just one thing, and we classify it as possibilities because we're discretizing it into different bins.
Oh.
I don't know if that makes sense. Like I'm thinking about the notion of probability. We've discussed many times on many episodes that probability doesn't really exist. It's just more of classifying our ignorance. And similarly, there's a connection. It's not exactly the same, but there's a connection between quantum mechanics and probability. And if probability itself is made up, then is the interpretation of quantum mechanics having all these different possibilities existing just a more fact of our own ignorance that like we just don't know what else to do.
I mean that is possibly true, but of course, once you dig into philosophy of science, I mean, this is just a hellscape. Like I don't even know where.
I would say it's the other way around, though, right? Like what we perceive as what we define as quote unquote probability theory is really derivative of the underlying laws of quantum mechanics, right?
Yeah.
Like, so like what we call statistics and probability is like a kind of imaginary structure that we place to explain the rules of this non-deterministic universe.
Yeah, absolutely. But I guess Sahil's question is sort of like, is this tainting our picture of these structures, right? I mean, I don't know at this point. I mean, this is just. I mean, you can certainly go full blown nihilist and just be like physics stuff doesn't make sense. But
yeah, but then you don't make progress.
Yeah, exactly. I think there's
a lot of people who just make a profession out of complaining about how things aren't being done right but don't make progress.
That's fair. That's fair. So we're basically at time, and so I wanted to give you guys a chance in our usual tradition to leave the audience with any words of wisdom that turtles standing on top of ever larger, ever smaller turtles have taught you.
Man, I've been trying to think of a closing statement this whole time, but I feel like this whole episode was a closing statement. So it's like, honestly, I'm more confused about this now than I was in the beginning. So I don't know if I can. I'll skip this time.
Is it fair to say there's no conclusion? It's turtles all the way. Maybe it's just keep getting confused. But I mean, I will say this. Like every time we ask these questions, I think a lot of times these questions, like you ask as a kid, it seems silly, and people just kind of like, oh, don't ask these. This is a silly question, But actually, there's a lot of depth in it. Even this lady in Mikey in the story, right? Come up to like a professor, philosopher, like, oh, could it be turtles all the way down? Of course, don't take it too seriously, but there's some nugget of idea there.
No, that's the beauty of the story. Yeah, I completely agree.
Exactly, like I don't know what the answer is, but I think it's worthwhile to keep thinking about it, and it's
the
crazy.
Old lady's guess was not a bad guess.
Yeah, but of course.
I just want to say, oh, go ahead, Tim. Sorry.
Yeah, I would say, but don't ignore the technical stuff, because while we're talking very colloquially, like there's like I think physics has the right way out. You know, we formalize these ideas, we formalize what self similarity is, and there is very rigorous math behind this. You know, very technical subjects, conformal field theories, and
Yeah.
the same subject can be used to describe materials and whatnot and phase transitions, and probably a few Nobel Prize here and there that came out because of some of the work. So this is a very legitimate, serious topic. And
we can characterize at least a few turtles with exquisite precision.
Was that all you had, Tim, or did
yeah,
you want to add
yeah.
anything else?
I guess in terms of human thought, I think we should be turtles all the way down. Never stop thinking.
Yeah. What do these turtles look like, though? That is the question.
Yeah. So we actually got an audience question at the very end. I want to read it to you guys, and then we can close it out. In this view of fractals, is it possible for the atoms, like our atoms, to be the solar system for someone else? I think I'm reading this question right. Effectively, you mentioned there's a connection between, like, the
Yeah.
Bohr model of an atom looking like our solar system. So can you, I don't know, I guess, like, can you say like our universe is like part of an atom of maybe something even larger? I don't know. I'm interpreting the question here.
I used to fantasize about that all the time when I was young. It's a beautiful idea, right? It's not impossible. Like, if it happens at a scale that's much, much, much lower than anything we have access to. Like Tim mentioned, this there's this relationship between small and large. Who knows? Maybe if we really looked into very, very small distances, we would see some kind of inversion. I don't know.
But for sure, we know that it's definitively not true on the most basic level, right? Like there is not planets at the size of atoms.
Yes.
Right.
But if you actually look close enough, you're going to make a black hole, and who knows what's in that black hole?
Right. In some weird way, in some abstract weird way,
it could be true.
There could be some truth to this. So.
Yeah, it's not crazy. I mean, not in the way that we think naively, but in a much more sophisticated way, there could be some truth to that, I think.
All right. I think this is a good spot to end this episode. A lot of really interesting things to think about. So yeah, so on that note, I want to thank everybody for joining us, and we'll see you all next week.
Yeah.